Okay, we're going to look at those torque problems from the torque problem set. The first problem, I don't have a copy to pull up, so this is just the torque problem set that's available in Classroom if you don't have a copy for some reason. If a bar on which parallel forces act is to be in equilibrium, which two conditions must be met? In order for that dynamic equilibrium of an object, we need to have the sum of the forces in the y direction and the sum of that's a sigma, the sum of the forces or the net force in the x direction. These both must be equal to 0. This tells us it's in translational equilibrium and will not accelerate in any direction x or y. Translational equilibrium. That's condition 1. Condition 2 is that the sum of the external torques, tau, external, equals 0. This tells us we're in rotational equilibrium. Rotational equilibrium. Okay? With this, we have a more full definition of what dynamic equilibrium is. Before we just said equilibrium is when acceleration is 0. That's our textbook definition. The textbook says, what is equilibrium? It's if and only if a equals 0. Okay, little a acceleration was from translational. Now we have alpha. Alpha as rotational acceleration. So we enhance and extend our definition of dynamic equilibrium to include both when alpha is 0 and a is 0. The other form of equilibrium we hear about is static equilibrium, and that's when something is still translating, but it's not accelerating. It can have a constant speed. That's what we mean by static equilibrium. These are our two conditions for dynamic equilibrium. That's part 1. Let's get rid of that. Or number 1. Number 2, a certain force is acting on a bar that is not at right angles to the bar. How is the torque in the bar produced by this force calculated? Let's draw a bar. There it is. We have a force. Let's draw a force in red. There's the force. And let's name our axis of rotation green dot. And it's coming out of the page at you as the axis of rotation. And so we expect to see some counterclockwise or positive rotation produced by the torque. The torque, which is in turn produced by this red arrow, which is the vector. That's supposed to be red, sorry. Red vector F, which is the only external force acting on this rigid rod, which will now rotate. So how do we say what the torque is? We say torque tau is equal to F sine theta, where theta is the angle in between the force F and the axis of rotation, times the radial distance r. This is the same thing. This is the same thing as saying F cross r, the cross product. Okay, this is what we see in the book, though. What I underline in green, what we see in the book is how we find our torque. Okay, so here is our sine, or here is our theta. Sorry, that's what we mean by the angle in between the axis of rotation and the force. And the component of force that we want to find, we'll do another arrow here. There we go. Is the one that's perpendicular to the axis of rotation. Okay. So it's the same here and here. These are the same lines. You see, I can construct a parallelogram just like we've had before, where the diagonal, in this case the hypotenuse is the resultant vector f in red, and I have two component vectors. So there's, oops, give me my pen back. So let's do it in pink. Would be my x component of the force, and in light blue I have the y component. So right here is f sub x, and here's f sub y. So f sub y is the one that is perpendicular to the axis of rotation, and this is a 90-degree angle here. So in order to calculate torque, we need to say that it's the f sub y times r. And we get f sub y, you can see, this is f sub y right here. It's opposite orange angle theta, the angle in between the axis of rotation and the applied force. So this is f sine theta, And F sub x, which isn't doing anything to help produce a torque, is adjacent to that angle. You can see that this angle is also theta. So we could say that this value is going to be F cosine theta. F cosine theta, because it's adjacent. Okay, so in our case, for this particular example, F sine theta in blue gives us our perpendicular force perpendicular to the axis of rotation. And then we would also need R. Where is R? Here is R, right here. That would be R. Okay? So that's what we have for number 2. Three is asking us to consider the necessary forces upwards on a bar that is being used to carry some weight somewhere near the middle. Not so much near the middle, in between, about a quarter of the way down the pole. Two individuals, Paul and Henry, carry a sack weighing 1.4 times 10 to the 3 newtons on a pole between them. If the pole is 2 meters long, the load is 0.5 meters from pole. What force does each person exert? So let's have a quick drawing of our rigid object. We'll have, let's call this guy Paul. Whoa, I'm sorry. I want a pen. This is Paul over here, and this is Henry over here. This length of the pole is 2 meters. That means this is 1 meter, right there, right in the middle. We aren't told that the pole by itself has a center of gravity or center of mass that's other than the middle. So if that's not given to you directly, it's a reasonable assumption that it's a rigid, uniform pole. And they're carrying a sack that has a mass, so I'll put mass S for the sack of grain or whatever it is that has a mass 1.4. Oh, I'm sorry, this is its weight. It said this is weight Fg. Fg of this sack, it weighs 1.40 times 10 to the 3 newtons. Okay. And it's 0.5 meters from Paul. So where's Paul? Paul is over here on the left. 0.5 meters is right here. It's in between. It's a quarter of the way of the length of the rod. So let's put in fuchsia. Here is my Fg of this sack. I'm not told anything about the weight of the pole, so it must be negligible. And now we have to ask, what are the forces being exerted by Paul and Henry? So intuitively, who do you think is going to be exerting a greater force? The weight on the pole is closer to Paul. The weight on the pole is closer to Paul. And so, from our experience, I hope, we've noticed something like this, that Paul's force upward is going to have to be greater than Henry's. Paul's force upward is going to have to be greater than Henry's. We'll check that. We'll figure out what the total must be. Now, if they're carrying this thing, then the pole shouldn't be moving based on their upward forces on the pole. It shouldn't be moving in the x direction or the y direction. So we look at our two conditions. One, the sum of the forces in the x direction should be 0, and we don't have any vectors in the x direction, so we don't have to worry about that. And then the sum of the forces in the y direction need also add up to 0. So let's look at those. We have the force of Paul, we'll call up positive, plus the force of Henry, must equal Fg, the force of gravity or the weight of the sack. So we know that force Paul plus force Henry must equal 1400 newtons. Alright, so here's one important thing we know. It's an equation we could come back to, because we have one equation with two unknowns, but if we can find out Fp or Fh, we can substitute it back into this equation. Let's call this equation 1. We can substitute it back in there and find out what the other force is going to be. So that's condition 1, looking at the sum of the forces in the x and y directions for rotation, or for translation. The second condition, number 2, is that the sum of the external torques must be equal to 0. So there's tau external must be equal to 0. So I need to look back at my drawing, which is very helpful, and say what forces are going to produce a torque. And this we mentioned the day we came back when this sheet was, after you'd already seen it for a couple of days, I'd sent it home with you. I think it was a Wednesday. I said our approach can be to pick an axis of rotation, because this thing isn't rotating if it's in dynamic equilibrium. It's not translating or rotating. But if the forces were unbalanced somehow, and there was some external torque, then it would rotate. So depending on which force is greater or lesser, or depending on the radius, that's going to determine the value of some torque that's acting on it. So it could happen that it could rotate, depending on what those forces and distances are from the axis of rotation. But we have to pick a possible axis of rotation. It's possible it could rotate it from many different points. Okay, so we can pick a spot that will be helpful. So we'll do a couple different spots. There are many different ways you could select a different spot for the axis of rotation. The one I'm going to select may not be the most helpful, but it is an example. I'm going to pick the point right here, where the weight is. Now maybe you say, though, that's not a good axis of rotation to pick, because we know something about that point. We know the weight right there. Well, okay. But this will just be to show that we can still solve the problem anyway, even if we pick this as the axis of rotation. So we'll try that first. And then with other problems, we'll look at finding axis of rotations from a different location. Okay, so we have our second condition that we need to satisfy, that the external torques are zero. That's where we were. So we're saying, now that this orange point is going to be the axis that I pick, say, what if that's the axis of rotation? Then that means that I have these two forces in blue and red that could produce torques. So for our red force over here, that's the torque it's going to produce is going to be a positive torque. And it's going to go counterclockwise about the axis. So it's going to be some force FH, the force of Henry, times the radial distance, times the sine of theta. Now these are both at right angles, so sine of 90 is 1. So we have the torque produced by Henry, which equals the force of Henry times the radial distance, which is the force of Henry times the radial distance, which is, we can see, 1.5 meters from that axis. 1.5 meters from that axis. So 1.5 meters times the force of Henry is the torque. That is the torque. And then we have a torque that can be produced by this force of Paul, the blue. And therefore that torque produced by Paul, we know it's going to be his force times the radial distance, which is going to be just 0.5 meters. Just 0.5 meters. So those in red and blue tell us our torques involved. The weight of that grain, represented by the fuchsia FG, it has a 0 radial distance, 0 meters from the axis of rotation, so that goes away. That's why we want to take advantage of picking a good axis of rotation to eliminate one of the unknowns. I eliminated a known in this one. You could have tried doing this if you didn't do it successfully already. Try picking a different axis of rotation from mine, see if things work out. So the sum of the torques, external torques, should equal 0. That's condition 2 of our dynamic equilibrium. So that means that we should have a positive torque from Henry, because remember, Henry is the H1, or the red one, is producing a counterclockwise torque, and the force of Paul, this is going to be a negative torque. It's going to be a negative torque going the other direction. So if the sum of all of the external torques adds up to 0, then I have the torque of Henry minus the torque from Paul must equal 0. Therefore, the torque of Henry must equal the torque of Paul. And we have values for the torque of Henry and torque of Paul. We have, for Henry, it's FH, F sub H times 1.5 meters. And we have the torque of Paul, which we said was force Paul times 0.5 meters. So I can solve for one of them, and maybe I can go back up to my equation here, what I called equation 1. from my translational equilibrium condition. So let's solve for the force of Henry, I guess, Fh. So then we get force of Paul times 0.5, force of Paul times 0.5 meters, divided by 1.5 meters, 0.5 meters. So then I have the force of Henry is going to be the force of Paul times 0.5 divided by 1.5. That's 1 over 3. Right. So let's just make it a little nicer to see. We say Fh equals Fp over 3. Okay, we'll make that our equation 2. We found a definite relationship between those two forces. So now we go back up to our equation 1, and we have a value for Fh. So let's substitute that in. Force of Paul plus what we've just found in green in equation 2, Fh is equal to the force of Paul divided by 3. Force of Paul divided by 3. And this all equals 1400 newtons. We got that from our condition 1 of translational equilibrium. So let's go up. We're saying that the force of Paul plus 1/3 the force of Paul, which should be equal to the force of Henry, will equal the total force of 1400 newtons, which balances out the weight translationally. So we're saying the force of Paul should be 3 times as great as the force of Henry. So there's the force of Paul is here, this distance from the weight, and then the force of Henry is way over here. So we're saying that Paul's force should be not just greater than Henry's, but 3 times, and you notice that that is the ratio of the distances. There's 0.5, and then from here the axis to the end is 1.5. So in order for them to balance, F force times distance equals force times distance. Alright, where 1 is the force of Paul, and the distance to the axis of rotation must equal the force of Henry times the distance to the axis of rotation. So we can get a number for that now. The force of Paul plus 1/3 the force of Paul is going to give us 4/3, right? Because we have 3/3 is equal to, this is like saying 3/3 the force of Paul. And I have 1/3 the force of Paul. I add them together, I get 4/3 Fp equals 1400 newtons. So I'll multiply each side by 3/4. And we'll be solving for the force of Paul. So we take calculator if we need it, 1400 times 7.5, we get 1050. So the force of Paul is equal to 1050 newtons. 1050, and we know from our equation 1 up here that the sum of the forces of the two individuals must equal 1400. So where this is the force of Paul, right here, the force of Henry's must be 1400 minus 1050, which is 350 newtons is the force Henry is pushing with. So those are our last two, those are our answers for that one. That's how we get there. So here we get this from the necessity of translational equilibrium is right there. Here we have condition 2, rotational equilibrium condition. That's all this stuff. Right, from that we got this equation. Alright, so we came from up here and we got this. We solved for one of the forces, the force of Henry, and we substituted that back into the translational equilibrium equation. So we could figure out what the force of Paul was. 1050 newtons, and force of Henry 350. Okay, so here's 350 newtons up here, 1050 over here. That's one way we can do it. And that was having picked an axis of rotation that for some reason I just decided to choose that one. Let's look at the next one. You can try that picking a different axis of rotation. For number 2, or I'm sorry, number 4, a uniform bridge is 80 meters long and weighs 34,000 newtons. What force must the pier at each end exert when a 14,000 newton car is 30 meters from one end? So I'll take this as my bridge again. And I'm just going to erase a little bit here. Oh, that's an object. Select that object. Whatever. I don't care. So let's say that this is we're told the weight of our bridge first. It's a bridge, it's got 2 piers supporting it and a car on it. The bridge is uniform, so that tells me that if it's a uniform bridge, then its center of mass is right in the middle. There's an equal distribution of mass for every area of its, for every cubic meter, right? It's got the same amount of mass in it. So the center of mass is right in the middle, and we're told that it has a weight that is known, and that is the weight we'll call W bridge, WB for W bridge. We know that number. We know that W bridge is 34,000 newtons. Okay. We know that it's 80 meters long. I will call that X bridge is 30 meters. And we know that we are looking for 2 forces. We'll make the blue the force of the pier on this side. We'll call it force 1. And then there's going to be some other force. I don't know what the forces will be, so I'm just drawing vectors of any length. But the pier number 2 on the right is going to be red. And we know that there is a car, 14,000 newton car, 30 meters from one end. So we know that there is a weight of a car, WC, which is 14,000 newtons. And we know its position is 30 meters from one end. So this whole thing, oh, I wrote this wrong over here. The length of the bridge is 80 meters. I'll fix that. Okay, and then we'll say the position of the car, I'll pick an end. I'll say the car is here. Right, so the center of mass, at this point the center of mass, this is the 40 meter mark. And so if I've just picked my car here, then this is the 30 meter mark. Right, and there's 20, and there's 10, and there's 60, 70, 80, and this little mark there would be 50 meters. Right? So I have a way of kind of pretend it's a meter stick if I want. So here's my car. That's WC. And now I have these 2 unknown forces. So I've got my diagram. I have a center of mass there. I have 2 forces by each pier. I ask myself, okay, so which value do you think should be greater? F1 or F2? The car, the weight of the bridge is right smack in the middle. So if you take the car off, both forces should be equal. Alright, if I moved if the weight of the bridge were acting at a center of mass closer to F2, right, if the weight of the bridge were acting here, and you had this instead, if that were for some reason more of the mass were concentrated on the right side, then F2 would be bigger. So instead, we have this car that's closer to F1, so we expect F1 to be greater than F2. So we're going to look at our 2 conditions now. Our first condition I can look at without yet thinking about an axis of rotation. Remember we said condition 1 is translational. The condition for translational equilibrium, which means the sum of the forces in the y direction must equal 0, and the sum of the forces in the x direction must equal 0. As before, we have no vectors pointing in the x direction, and for y, again, I call up positive. So if all of those must equal 0, I have positive F1 plus positive F2 minus the weight of the car minus the weight of the bridge. All those have to equal 0. So I can clean this up a bit and get rid of my negatives. Or, conceptually it helps too. My upward forces equal the sum of my downward forces. Okay, so we can go ahead and let's make this fuchsia equation 1. Because we know we have the measurements for WB and WC. So we actually know that this must be equal to 34,000 plus 14,000, which is 48,000 newtons. So we can come back and we say F1 plus F2 will have to be equal to 48,000. Now we know something. Okay, so that'll be an equation we hold on to. Condition 2. Condition 2, we're going to look at the... whoops, that was a bit much. We're going to look at the sum of our external torques. Look at the sum of our external torques when analyzing rotational equilibrium. Rotational equilibrium. The sum of the external torques should be 0. So we go back and look at our torques, and we say, aha, we got to pick an axis of rotation. This time, I'm going to pick, I don't know, F2. Alright, this is going to be, the point where F2 is applied is going to be my axis of rotation now. Axis of rotation, because I feel like it. Okay. So, because that's the axis of rotation, F2 does not produce a torque because F2 is a radial distance from the axis of rotation that is equal to 0. Now we do have other forces. Now remember that counterclockwise is positive direction by default, unless we change it. We can change it. You could say it's negative, you just have to be consistent. So let's say that the counterclockwise rotation is positive, so that means that WC must be positive. The torque produced by WC will be a positive torque. The torque produced by WB will be positive, and the torque produced by F1 will be negative. Okay, these are for my torques. I'm keeping it in green. These are torque directions. Alright, F1 has a positive translational direction. Up is positive, down is negative for translation. Counterclockwise is positive, clockwise negative for rotation. So I have a positive torque produced by WC. I'll start with my positives. So I have, let's write these out as torques first. So I now have a torque produced by the weight of the car and its distance, plus a positive torque produced by the bridge's weight and its distance from the axis, minus a torque produced by, I'll just call it 1, because it's the torque produced by force 1. And all those have to equal 0. So I can say TC plus TB equals, or tau 1. Tau C plus tau B plus tau 1. So now the torque from WC is going to be WC, the weight of the car, times the distance from the axis of rotation. So it's my distance, there it is. It's 40 to the halfway point. Right, it's 40 to the halfway point, plus right here's another 10 meters, right? Okay, so it's total 50 meters from the axis of rotation I picked. So torque of the car is going to be weight of the car times the sine of the angle between the axis of rotation and the force. And they're all at 90 degrees again, so sine of 90 degrees is 1. So you have the weight of the car times 50 meters plus the weight of the bridge times 40 meters, because that's concentrated, the center of mass is right at the center of the bridge, equals F1, which we don't know, times, it's all the way on the other side. It's the full 80 meters. Right? So now, because I know the weight of the car, I can put these values in. So there's 14,000 newtons times 50 meters. So we got newton meters for torque. And then I have weight of the bridge, which is 34,000 newtons times 40 meters equals F1. And if I just divide by 80 right now, 80 meters. So notice my units, for my units I'll have newton meters divided by meters. So my meters will go away and I'll be left with newtons, which are the units I want for my force. So let's calculate that. Come on, calculator. So we have the weight of the car, 14,000 times 50 plus 34,000 times 40 equals divided by 80. 25,750. I hope that's right. That seems... I think that's reasonable. 25,750. Right, because what do they have? It has to add up to 48,000. So they should be about equal, but a little different. Right, so they got to add up to 48,000, and both forces should be not equal, but they should be too extremely different. So this seems like a reasonable answer. I'm going to box that for now. I need units. Newtons, right? And I need to consider significant digits. Consider sig figs, which I don't have the problem in front of me, so I don't actually know how many. But I think it's 3 in this problem. Well, you know how to figure out significant digits, though. So 25,750. We said that is F1. So let's go right here and let's say F1 equals 25,750 newtons, which means F2, watch, F2 is the red one, whoops. That's F1. F2 is going to have to be, like we said in this equation, yeah, F2 is red. We have to, like we said in this equation, fuchsia right here, we have F1, we just need to find F2, and they must add up to 48,000. So this must be 48,000 newtons minus 25,750. So that is 22,250. Alright, I'm tired. Let's check. It's almost embarrassing, but it's okay. It's never bad to use a calculator. Check your... Our brains get tired, right? 22,250. Okay. Yeehaw, I did it. So I wanted this in blue because this is my force 1. Okay, and then we round... I don't remember how many significant digits. I think it's 3. Right? So then the answers should be... I look at my third digit, so I have 25, 8... And then if I round this, I'd have 22,300. But this guy, the sum of them has to be 48,000. So the answers I boxed really make more sense than rounding here, doesn't it? Because this would then just be 22,200, so that it adds up to 48,000. But significant digits aside, because we only kind of care about them. They're not as important as actually understanding what we're doing. So there we get 2 forces. So quick review. How did we do that? We drew a picture. That was a very good idea for us to see what's going on and see where our measurements are, the length of the bridge, halfway point where the center of mass is, where's the car. Notice I just picked one end to put the car on, and I picked the one closer to the larger F1 because I drew that a little larger. That's the one I chose to put the car closer to. I had my known stuff up here, right? I listed out my known stuff. I made sure I got my units there. First I wrote the mass. I wrote the mass of something, and I was like, no, that's the weight. You gotta be careful. Or maybe that was the last problem, but we get anyway, if it's weight, we got newtons. Remind myself of the distance of the bridge. I called it a variable that I didn't need to use. And then once we have this picture set up, it's easy for us to go to our 2 conditions for dynamic equilibrium. Condition 1, translational equilibrium. Again, sum of the forces in the x direction. This didn't matter because we had no forces in the x direction. So we just looked at our y's. Okay. I called up positive, down negative, so we end up with our first helpful equation. We'll call it fuchsia equation 1. The sum of F1 and F2 must be equal to 48,000. And then the second condition, our torques. All our torques are over here, torque calculation. So we're looking for a net external torque of 0, unless you want this bridge to rotate and have the car fall off. So then we have a solution looking for F1. This is what we were solving for. Okay, so it's good to set it up like this. We say what our torques are. We make sure we look at clockwise and counterclockwise, so we have our signs. Our sign usage is good. Then we say, okay, what are the force cross, radial distance, and our sine of the angle is equal to 1 because they're all perpendicular. Then we substitute in values here, solve for f, and we get our value for f1. And then we get to take f1 back up here to our fuchsia equation 1. And we can solve for f2. That's what we have for that guy. Let's look at number 5. Back to the top. A bar 6 meters long and weight 400 newtons has its center of gravity 2 meters from one end. Alright, so here's my bar. It's still right up there. And it's 6 meters long. Okay, so I'm just going to say x bar. This represents my length, because I use x for that. Alright, it has a weight. Weight of the bar is equal to 400 newtons. Get my known data. And this bar has its center of gravity 2 meters from one end. 2 meters from one end. So it's 6 meters long, so all this, right, this is all 6 meters. And then located 2 meters from one end is where the bar's center of gravity and center of mass are. 2 meters from one end. So this is 3 meters, that's halfway. Say that's 2, 1, 0. Trying to split it up well. Okay, so this is my 3 meter mark, 2 meter mark, 1 meter mark. So let's say 2 meters from this end is my center of mass. Remember where the gravitational field strength, or the acceleration due to gravity, g, is constant. And for the most part it is for all of these problems we're looking at. It's different for a satellite. But for us, around the surface of the Earth, little g is little g. The center of mass and center of gravity are at the same point in the object. So this is before we hang any stuff on it. That's where the bar will balance. If you put your finger right here underneath the 2 meter mark, I mean it's a 6 meter, the thing's over 18 feet long, but if you had a fulcrum that you placed right here, that's where it would balance. So that's the problem. It says its center of gravity is there. That's also the center of its mass. So that's what we mean by that. And there is a weight of the bar. This is WB then. Oh my goodness. Which we called, the problem says is 400 newtons. Right, so weight of the bar is concentrated there. That's where we say wherever the center of mass is, wherever the center of mass is where the weight of that object is said to act. Because there's mass distributed throughout the entire object. So it's like you're saying, this is what we don't do. We don't say there are a bunch of little force of gravity vectors acting on the infinite number, not truly infinite, but the might as well be infinite number of atoms in this thing, all pulling down. We just locate the center of mass, and that center of mass is the place where... Did this thing just delete all of my stuff? Oh, good God. That center of mass, it's okay, here we go, which is 2 meters from the end of a bar, is where we say that the weight of this bar is concentrated. And we said the weight of the bar was 400 newtons. And the length of the bar was 6 meters. And now this is going to be our bar. Where is that button? Don't hit that button again. Okay. Alright, I guess it's this color now. What's next? A 450 Newton weight is attached 1 meter from the heavy end. A 450 Newton weight. So let's call that weight 1. Weight 1 is 450 newtons. And then there's another weight, weight 2. I call weight 2 is 550 newtons. We got everything labeled here. Okay, so it says weight 1, the 450 Newton weight is attached 1 meter from the heavy end. 1 meter from the heavy end. I drew my bar improperly. Look, I put the center of the mass right in the middle. Okay, what? Gosh sakes, I don't really see how this program is of any value. I'm sorry. Let's cut. Let's just draw a line, because that I know I can do. So we're 2 meters from the end of our bar. Okay, and this whole thing is a 6 meter length. So we say weight 1 is attached near the heavy end. So where's the heavy end? Where is the concentration of mass? It's closer to this end. That's the heavy end, and this is the lighter end. Right? The center of mass, the center of gravity, the point where it's going to balance, if that's where you put the fulcrum, that's going to be closer to the heavier end. Same thing if we take a regular meter stick and we add a weight on one end. We have to move the fulcrum closer to that end in order for it to balance, because that's become the heavier end. And it is producing now a greater torque if the fulcrum's right in the middle. So you need to move the fulcrum closer to that weight, or closer to the center of mass. And when it's right on that center of mass, if it's just the bar by itself, then it will balance. So we know the heavier end is on the right. And then we have another weight that I called weight 2. I said it was 50 newtons. Is attached 1 meter from the light end. So, let me draw in pink we'll draw my weight 1. 1 meter from the heavy end. And then in blue, that's from the heavy end, right? And then 1 meter from the light end. 1 meter from the light end is right here, and this is larger. This is 100 newtons more. Right? And we should say, in pink we'll say this distance is 1 meter. And blue to go with this one, this distance is 1 meter. And we see 2 meters is our center of mass, and the whole thing is 6 meters. Anything else? What force must support each end of the bar to produce equilibrium? So now these are the forces we're looking for at each end. So there's F1. I don't draw these to scale yet. I don't know what they are. Might as well make them look equal. So you might have an idea intuitively, which force should be greater? It's a little difficult now, though, because the center of gravity is different and the mass is different. Okay, so same approach. We'll look at our 2 necessary conditions for us to find these 2 forces. So what conditions do we need for dynamic equilibrium? Condition 1 is translational. Some of the forces in the y must be 0. Some of the forces in the x must be 0. Do we have any forces in the x? No. Forces in the y, yes. We call it positive down negative. So we have F1 plus F2 must equal our downward forces, weight 1 plus weight 2 plus weight bar. Right there. Let's see what we know. We know all of the weights, 1, 2, and weight B. So we might as well get a value for this. We have 400 plus 450 is 850, plus 1550, or plus 550 is 1400, right? So here we have, this will be, yes, our fuchsia equation. Pretty sure that's 1400. This is our first equation that can be useful. That tells us something about the relationship of the 2 forces we need to find. On its own, it's not enough. It's not enough to know exactly what F1 and F2 should be. So we have, that's 1400. Okay, good. So condition 2, we're used to this now, right? Condition 2, the sum of the external torques external equals 0. Okay, so I called up positive, down negative for translation. Let's remind ourselves counterclockwise is positive. And I need to pick an axis of rotation. So I can try, you try whatever you want. Generally, if you notice, when I pick that axis of rotation and place it at F1 or F2, that eliminates that value of force that is capable of producing a torque from the equation, since the radius of that distance, the radial distance of that force from the axis of rotation is 0, so that the torque it produces is 0. So let's keep doing that. Let's, I think I did this last time using the location of F2 on the right side as the axis of rotation. So I'll pick F1 this time. Let's see if hopefully I get the same answer. Pick that as the axis of rotation. So the torque produced by F1 is eliminated from this perspective. So what do we have? We have our bottom, so which way, this is the way it will actually, okay, got it. So F2, this will be, let's put it in green like I did last time. F2 will be producing a positive torque, right? That's counterclockwise, and then weight 1, weight B, and weight 2 will all be producing the opposite of what I just wrote. I'm thinking negative and I write positive signs. Right? Those are all producing clockwise motion, and then F2 is going to produce a positive torque. So they're competing against one another, and we need them to balance out so that there's no net external torque. So here we go down to our torque equation. What's positive? Torque F2, or you know what? What did I do last time? Just torque 2. Torque 2 is positive. That's produced from F2, and then the rest of them are negative, minus the torque of weight 2 minus the torque of weight 1 minus the torque of the weight of the bar. Alright? And that all equals 0. Oh my goodness. So let's see what we got. We have torque 2 is the product of force 2, and since it's at a 90-degree angle, we have no issue of finding its component. So it's force 2 times its radial distance from the axis of rotation. That's the full 6 meters away. So that's times 6 meters. Minus, I'll just cut a shortcut and say that's equal to these 3 torques if they're added to the other side of the equation. So we can keep everything positive. Save us a step. So I have the torque of weight 2 is the value of weight 2. So it's just right now W2 times its radial distance. Where's weight 2 located from my orange axis? It's only 1 meter away. It's 1 minus the torque of weight 1, which is weight 1 times its radial distance. Where's weight 1? It is 5 meters away from my orange dot. Okay, so that's times 5 meters. Minus the torque produced by the weight of the bar, which is, that's right here, right? So this is 4 meters, so it adds up to 6 total. So that's the weight of the bar times 4 meters, minus the weight of the bar times 4 meters. Now, if I want to find F2, I need to divide both sides by 6 meters. And I also need to substitute in the value of my weights. So weight 2 is 550. So 550 times 1 is 550 Newton meters. Weight 1 was 450, right? So 450 times 5 is 450 times 5. Is it 5 or 4? It's 5. Yeah, it's 22,500, so 22,500. Oops. Sorry. Yeah. I need to get rid of a... Come on, there we go. Newton meters minus the weight of my bridge times 4, or the bar, weight of the bar. 400 times 4, so it's minus 1,600 Newton meters. Okay, and this is all divided by this value here. Divide both sides by 6 meters. We get Newton meters divided by meters is newtons. So let's look at that 550 minus 2250 minus 1,600. Why? What did I do wrong that I have a negative value right here? These are all positive, because I moved them to the other side of the equation. But I reread the negatives because I'm not paying attention. So this is, let's just do it all the way. 2250, 1,600. Okey-doke. And then we have divided by 6. 733 1/3. So F2 is 733, rounded newtons, are positive, that's good. So we're saying that the heavy end is 733 newtons. And we also have, back to our equation 1, our fuchsia equation. We said that the sum of these forces must be 1400, so we said F1 plus F2, whoops, we know F2, what are you doing? Plus 733 newtons must equal the total 1400. Now we get this from the condition 1 of translational equilibrium. So F1 is 1400 minus 733, which is 667, right? Right, let's just check, because I sometimes need to. Yep. Oh, of course. Now the problem had described things in terms of the heavy end and the light end. So we can see that my heavy end I had in burgundy is next to F2, or brown, whatever it is. F2. So F2 is heavy end. F2. So this is force at the heavy end. This is force at the heavy end. And then I need to have, I need to say, I said this light blue was light. Right? Light blue was light, so I have 667. And then the number of significant digits, I forget. I think it was 2. So we'd have 730. Whoops, wrong color. But you see what we got here. 730 newtons if we round it. So force at the heavy end equals 730. That's a 3. That is a 3. We round it down to 730. And then the force at the light end should be 670. If we round it to 2 significant digits. And so we have 730 and 670. Those add up to 1400. Same process there as last time. You pick, we get a picture. We say, what do we know, what do we don't know? Very good. We need to illustrate those distances so we can calculate the torques. Remember, if we're told, when they're told in that problem that we were told the center of gravity was located here. Okay, so they're saying this bar, like you're given imagine you're given a meter stick, and you expect it to balance right in the middle. So you put your finger there and hold it right in the middle, but it doesn't balance, and it torques and rotates and falls off your hand. And you say, well, that's odd. So then you say, I wonder where it balances, and you slide your finger down one end, and it keeps falling everywhere, down that end. So you slide it down the other end, towards the heavy end. Okay, and eventually you get to a point maybe 20 centimeters away from the heavy end, and that's where it finally balances. You say, oh, okay, this is the balancing point. That's where the center of gravity is. That's where the center of gravity is. And that is also where the center of mass is for that non-uniform meter stick that you're holding. Because center of gravity and center of mass for everything we deal with as just a particular object that doesn't have anything hanging on it, or you haven't messed with it, just like this meter stick example that's non-uniform, center of gravity, center of mass are in the same position. Right, then we start hanging stuff from it. We have these 3 weights, the weight of the bar, which is concentrated at the center of mass. Center of mass is the point that we say, that's where you can draw your force vector, the weight vector of that bar, is at the center of mass. That's where you get to draw that. Then we have a weight 2 that is hung near the light end, and a weight 1 hung near the heavy end, and the 2 forces, we're told, what must the 2 forces at the end be to balance it? Same process we've done with the others to get there. 2 conditions for dynamic equilibrium. Let's look at the next one briefly. These, you should be seeing a pattern here. These are all using the same approach. A bar 10 meters long has its center of gravity 3 meters from one end. If it is placed on a pivot 3 meters from the light end, it is placed on a pivot 3 meters from the light end, and a weight of 740 newtons is hung from the light end. It will balance. What is the weight of the bar? So now we're just given different stuff, but doing the same thing. This is our bar. Here's our pivot. Here is some weight it's weight at a heavy end, right? It's placed on a pivot 3 meters from the light end, and the weight is hung from the light end. Okay, yeah, so this is our light end, so let's put weight light, which equals 740 newtons. And then we have, this is a 3 meter length here. And then I have a weight that I will do in red, which it says is from its center of mass, which is 3 meters from the heavy end. Heavy end is the end with the center of mass closer to it. Right, so this is the weight of the, what is this thing, a bar? Yeah, weight B, so weight for the bar. So it's 10 meters long. Remind myself, X bar is what I call it. Total length is 10 meters. Okay, 3 meters from the light end is the fulcrum, shown by my triangle. 3 meters from the other end, hold on one second. If it is placed on a pivot 3 meters from the light end, and a weight is hung from the light end, it will balance. Yes, so here, this is important for me to say, this is the center of mass and the heavy end. That's what I need to do to remind myself. This is the light end. Okay. So without these weights, I mean, there's just one weight hanging from it, but without this weight at the light end, if you took that away, the bar would not balance on this pivot here. If you took this weight away, you would have to move the pivot, the fulcrum, the triangle, whatever, the string that it's hanging from would have to be there in order for it to balance. But it's not. You've moved it so that it's over here, and now in order to make it balance, you need to hang this weight at the light end of 740 newtons. And so the problem is asking, well, what must be the weight of the bar, which that weight of the bar acts at the center of mass. What is the weight of the bar? So there's one more force I need to draw when I have this set up. I have a normal force here. Otherwise, you see I would have a net force in the negative y direction if negative's down. So I have some force normal here that's preventing it from falling. And that would be part of my condition 1. We have nothing to look at in the x direction, so some of the forces in the y direction must be 0. So I have force normal positive must equal the weight at the light end plus the weight of the bar. And I don't think I really care about the normal force in this problem, but that is condition 1 for translational equilibrium. Condition 2, sum of our torques external must be equal to 0. Let's remind ourselves counterclockwise is going to be positive. That's a 3, not a plus sign. That was strange. And we'll choose the actual pivot point to be the axis of rotation. And we don't know anything about, I mean, the normal force isn't producing a torque there. And we have a fulcrum, that's the place it would pivot, so why not choose that as our pivot point, or axis of rotation rather. So the sum of the torques I have, my weight at the light end is producing a positive counterclockwise torque. Okay, so let's say weight at the light end is positive, and times its distance from the pivot, which I think is 3 meters without scrolling back on it. This L is too big. Hold on a second. The weight at the light end times 3 meters from the pivot is the torque of the weight at the light end, and it's positive counterclockwise. See that? And I have a weight over here in red, the weight concentrated at the center of mass, the weight of the bar, is trying to produce a negative torque, so that'll be minus weight B times its distance. So this is 3 meters from one end, this is 3 meters, this is 3 meters, that's 6. My remaining distance here to here is 4 because it's a 5 meter long bar. So the distance of the weight from the axis, the distance of the weight of the bar from the axis here is 7 meters. So that's 7 meters I need to show the weight, the torque produced by the bar. It's the weight of the bar times 7 meter radial distance. They're both at 90-degree angles. Sine of 90 is 1. So I know